This is the Bendix G-15, a full-fledged vacuum tube computer from 1956, and currently, I do believe it is the oldest running digital computer in North America. That's pretty... What? Will it play Doom? Wait, what? Doom, will it play it? No, it's from 1956. All right, that was a little weird. Anyways, as I was saying, can it play Doom? Can it play Doom again? It's a vacuum tube computer. Like, no, it can't play Doom. Can it play Doom though? Wait, what? When will it play Doom? Can it play Doom though?
これで Doom をプレイできるかな?
Can it play Doom? You guys are acting like I'm just gonna walk over there and hit go and the thing is just gonna play Doom. As I was saying before our impromptu jam session there, this is the Bendix G-15, a full-fledged vacuum tube computer from 1956. And I do believe that this is the oldest running digital computer in North America. Or at least I haven't seen any evidence to prove otherwise. Now, this machine is currently on loan from Bob over at System Source Museum. And if you haven't heard of System Source Museum, go check them out immediately. They're one of the greatest computing history museums in the world. And Bob is an absolute legend because he loves to see these machines come up and work and let people get hands-on with them, which is exactly why he sent this G-15 all the way down here to Texas so we could get it up and going. And as you just saw, it is going. It plays Doom. That's right, Doom will run on anything, including the oldest digital computer in North America. But the journey to get it to the point where it could play Doom was arduous, to say the very least. Now, we have about 15 episodes covering all of the effort that went into getting the hardware to this point, but up to now, we haven't done any talk about the software. And that is just as obtuse and foreign and wild as you would imagine. So buckle up, because today we're going in deep onto the software that was required to get Doom to run. First things first, how are we even hearing music come out of the G-15? A lot of people think we're doing the old RF trick where you put an AM radio near the machine and then you feed it specific data that generates RF noise that the AM radio picks up, but we're not actually doing that. Instead, we've actually modified the machine a little bit. Now, this is not something that we came up with on our own. We found some original Bendix documentation that outlines this modification. And what you do is you take a wire and you solder it to the right amplifier of line 2 and the reed amplifier of line 3. Then you run these through some coupling capacitors, then some big resistors, and out to an amplifier. And I actually have a little board in here that does just that, and there's a little header on the bottom of it that I can plug this cable into. And on the other end of this cable is this little plug right here, which just plugs into any amplifier out there. So when you hear this thing playing Doom, you're hearing the real deal, legitimate ones and zeros written down into memory. You're hearing the raw binary. Also, that doesn't really make a whole lot of sense because if I lay a value down into memory, that's kind of a static thing. That's not really going to sound like music, right? Well, this uses kind of an unconventional memory system, something called a drum memory. This is actually kind of similar to like a modern spinny hard drive, only instead of a platter, it's just like a big wheel thing that's spinning in a circle. And the data that's laid down onto this drum is laid down in a bit serial fashion. And because the drum is spinning at a known speed, 1800 RPM or 30 revolutions per second, we can lay down data with specific zeros and ones in a set pattern that actually comes out like a square wave in the audible range. And we did all of this pretty much so we could run the music program and ultimately load in Silent Night so that we could get Christmas music playing for the Christmas special. And Lloyd, who's an absolute legend, went through a massive amount of effort to figure out the exact ones and zeros to lay down to play specific notes and custom programmed up Silent Night. But if it was that much effort to write Silent Night for this machine, how much more effort is it going to be to write Doom? Particularly for someone who is not a very good programmer like me. And the truth of the matter is that I don't have the programming chops to have written Doom for the G-15, but that raises a bit of a problem. Not only is this the oldest running digital computer in North America, it is the only running Bendix G-15 anywhere in the world. Which means that if you don't live in the middle of nowhere, Texas, and know me personally, how on earth is it even possible to write new software for this machine? Much less software as complex as Doom. Well, it turns out that a very brilliant individual by the name of Paul has actually made a Bendix G-15 emulator, and it's web-based. So if you want to sit down and start writing new software for the Bendix G-15, you can do that today by just going over to Paul's website and loading up the G-15 emulator. And an absolute legend by the name of Bill did just that, to start writing new software for this G-15 that ultimately led into him programming Doom. Now, there's no way that I'm going to be able to do Bill's story of how he got there justice. So let's get Bill on the horn and hear it straight from him. Bill, thank you so much for taking my call. How are you doing today?
I'm doing great, thanks. Thanks for having me.
All right, so we're going to talk about programming a machine that's like 70 years old from the 1950s, but this is not your first foray into programming. Like, what do you normally do?
Well, I've been a programmer for basically my entire life right now. I started in the 80s, and I'm currently teaching computer science at the Vermont State University.
Before you wrote Doom, you got inspired and did some hacking around on the emulator, right?
Yeah, it was right after your Christmas episode when you had played that music. And on your Discord, some folks were talking about the fact that they were having trouble using the emulator. And I started up and started hacking on Paul's emulator. It turned out there wasn't a problem with the emulator at all. It was just, your standard user error. Then, after I had it working and was loading and running software, I thought back to the music and decided to try hacking in music playback functionality to his emulator. Likely before long, my changes will actually be merged into his code, so the version that he hosts will play audio back if anyone wants to try it.
And then once you had it playing back audio, you actually discovered some songs that we had missed somehow with the music playing program, right?
Yeah, I downloaded that same music program and started looking at how it worked. And if I remember right, you had said in the video, and there's a few more programs on this tape that seem to just crash. And once I started to learn my way around, I thought to myself, well, wait a second. Those might not be programs that crash. They might just be music data ready to play back. So I did a little virtual cut and splice on those tapes. And yeah, found 3 or 4 new songs on one of those tapes we didn't know about. With that loaded, I'll turn off Enable and hit Go.
Now, there are only two games that I play beginning to end every single year since they released, and one is Full Throttle and the other is Doom. And I'm actually like legitimately in the middle of another Doom 2 full playthrough right now, doing it in between bursts of editing whenever I need a break. And it's every bit as brilliant as it has been for the last 3 decades. But every time you guys leave a comment on one of the machines in here asking if it can play Doom, it always pains me a little bit because I would love to be able to play Doom on the Centurion or on the PDP-11 or the Bendix G-15. However, you guys didn't specify. You didn't say, can it play the video game Doom? You only said, can it play Doom? And the G-15 is legitimately playing Doom.
You are technically correct. The best kind of correct.
However, in order to get it to play Doom was not easy. We could get it to play Silent Night, and if we take a look at the sheet music for Silent Night, that's a pretty simple program. But if we look at the sheet music for At Doom's Gate, or the E1 M1 theme song, yeah, there's a big difference there. So actually the music playing program that we used to play Silent Night was not gonna cut it here. We had to go above and beyond.
Each note was saved on one of the memory lines as a sequence of long runs of ones and then long runs of zeros, repeating to build a square wave. That's great when you have a simple song like Silent Night that you can fit into about 15 notes. The Doom music has at least twice that many notes, plus a bass drum and a hi-hat. So fitting all of the different notes onto the G-15 was the first problem I had to come up with a solution to. The second issue is that some parts of the song are much faster than Silent Night. The arpeggios, where the guitar shreds in the original version, just go way faster than that original music program was really prepared to play back. The song itself is quite a bit longer than Silent Night, and although I'm only playing a short part of the song on the G-15, even that was quite difficult to fit in, given how much more complicated it was than the simple Silent Night song we originally saw. The G-15 has 18 general-purpose lines of 108 words each, and I ended up using them all to fit the program in there.
Programmers like to separate languages into kind of two distinct categories, a high-level language and a low-level language. But as with most things in life, the deeper that you look at something, the more of a spectrum it becomes. Now, a high-level language is going to be something like BASIC, and this creates pretty human-readable code, but we don't actually know how that code is interacting with the hardware underneath. But if we do want to actually interact with the hardware at a more intimate level, that's where something like assembly comes in. And I can do things like tell it what value to store in a specific register in the CPU or where to put values in memory. But for the G-15, I feel like we have to go even a little lower than that. And in order to understand how we're going to write software for the G-15, there's two big hurdles that we got to tackle. And the first is how do we interact with the drum? The second is how do we build an instruction? Now, if we look through the manual, we can find this section here that says the memory consists of 21 long lines of 108 words each, 5 short lines of 4 words, 3 short lines of 2 words each, and 2 short lines of 1 word each. Now, what is this long line versus short line thing that we're talking about? Well, that has to do with how the drum is actually arranged. Now, if we're laying down 108 words of data onto a long line, that happens at the long line right head here. And then as the drum rotates all the way around, we come back around to the long line read head. The data is picked up 1 bit at a time by the read head and then laid right back down 1 bit at a time by the write head. However, there's this weird no man's land in between the long line read head and write head that has a couple of permanent erase magnets hanging about. As that magnetic material slides underneath the permanent erase magnet, it gets demagnetized, and then we run into the 4-word write heads, and they can write down new data in these shorter, smaller memory locations. all followed by the short line read heads, which are all in the exact same place. And then of course that magnetic material is going to keep swinging. We hit another permanent erase magnet and we're back to the long line write head. So what we're doing is we're using about 3/4 of the drum to store long line information. And then that remaining pie slice that's in no man's land, we use to store rapid access information. So it's important to note that everything is on the drum. Our program that we're executing is on the drum. Our data that we're manipulating is on the drum. The CPU registers are on the drum. The drum is the heart of the machine. Now, I said everything is on the drum, but that's not actually true. There's one little piece of this equation that is actually built out of vacuum tube memory, and that is the instruction register. So an instruction is stored on the drum, but it's read off the drum one bit at a time and shifted into a vacuum tube shift register that contains the 29 bits that get decoded to tell the machine what to do. And this is actually how we write instructions for the machine. Although Bendix likes to write things in decimal where possible, and they rearrange the order of this a little bit whenever you're actually writing the equivalent of Bendix assembly, which would then be assembled by PPR, or the program preparation routine. Now, the way we're actually going to construct an instruction here is using this layout. The location is the word position of the current instruction on the drum from the line that we're currently executing. The prefix indicates whether this is a block command or a normal command. If it's a block command, it means that we start executing the instruction immediately and we don't stop executing until we get to timing mark T. Now, this can be very helpful if you want to copy entire lines from one place to another. But a normal command or a deferred command is where we don't execute until we get to timing mark T. And this is the word position that we're looking for. Then after that, we have the next command. This is the word position on the current line that we're executing from of the next instruction. This is effectively like having a go-to in every single line of code. We have to think about where the next instruction is going to be physically located on our spinning hunk of metal down there. The next three characteristics, source and destination, are all very closely related. So the timing number is the word position on the line, and then we tell it which line we want to pull from and which line we want to lay it down on using the source and destination. But if we want to modify that data, we use the characteristic bit. And this is already getting confusing, and we're not even to the hard part yet. If the source or destination is set to 31, we get into this realm of weird specialized instructions. For example, if we want to do multiplication or division, we set the destination to 31, and then we set the source to 24 or 25. If I want to read typewriter input, set the destination to 31, set the source to 12. Or if I want to halt all of this because my brain is starting to explode, I set the destination to 31, I set the source to 16, and the whole thing comes to a halt.
So I wrote this basic Fibonacci program and started to learn my way around the G-15. This code is easy to read, but it was written before I learned how to time the code for performance. Instructions 8 through 10 perform the addition where the new number C gets assigned the value of A plus B. Instruction 8 loads the value A to the accumulator. Instruction 9 adds the value B to the accumulator. And then instruction 10 stores that result back to memory. But if you look at the locations and timing numbers on this, it actually runs quite terribly slow. So the first instruction at location 8 can't even execute until the drum has spun around to that location and 8 becomes available to read. But when does that instruction execute? It's set to execute at time 30. So it's rotated around to 8 to get to this instruction, and then has to wait until instruction 30 to be able to execute the instruction. Well, what's the next instruction I told it to use? It's instruction number 9. And we just went from 8 all the way to 30 to load that value. And now we've got to go back around the horn past 8 to 9 to get to the next instruction, where I'm asking it once again to load another value and add that to the accumulator. So just to do this C equals A plus B, we've basically gone around the drum 3 times. It only spins 1,800 times a minute. we've wasted 1/10 of a second just to add together 3 numbers.
But you can write it in such a way that you get the whole thing done in a quarter revolution, right?
Or less. What you do, if your instruction is at location 8, the earliest it can start executing is location 9. So hopefully, that's where the data you want to load is. So if instruction 8 says at time 9, load a value to the accumulator, it gets done in 1/108th of a revolution. Ultimately, though, sometimes the data you need just isn't where you want it to be, and you have to take a longer wait for the drum to spin around to where you need it to be before you can read the data and do something.
When you were programming this thing back in the 1950s, Bendix had like a programming sheet, right? That you would write down and fill in what locations have been used.
As you wrote each instruction, or piece of data, you'd cross off those locations on a grid on the side of the sheet so you could see what you'd used. And when you're going around the second time, you could fill in the blanks. I'm not sure I understand how people could see that far ahead and plan to make things perfect. Maybe they couldn't, but they did a good job of it with what they had.
I've got the raw binary for Bill's Fibonacci program loaded up here, and we can see that it's pretty short, so let's punch this out and run it on the real machine. And in order to punch it out, I'm just going to hop over to Terraterm here, and we'll go File, Send File, and that is Fibonacci BCD. I'll tell it that's a binary. I'll click Open, and this thing should start going. There it goes. Punching it right on out. We got a nice long leader going on. Now we got our data showing up here. It was a little longer than I was expecting. That's a decent amount of tape that has created a bit of a mess. But let's go ahead and rip that off. We'll get this spooled up onto the real machine and give it a test. Since the Fibonacci program is pretty short, I don't want to load it up onto one of these cartridges because I only have 2 of these and I want to save these for the longer programs. So we've got this little 3D printed piece here and we're just going to kind of do this by hand. To get this going, I'm going to flip the enable switch to on. I'm going to hit P, and it's going to start reading in off of the paper tape here. Now I need to go enable switch off and go to go, and it's going to read in the rest of the program here. And as soon as it gets done reading in the full program, it should start typing Fibonacci on the typewriter. And yeah, there we go. 1, 2, 3, 5, didn't print very well. There we go, there's 13. I apologize, the typewriter's a bit of a hot mess right now. We're gonna get into that in the next episode where we start working with intercom. But we can see that the numbers that do actually print out seem to be printing out correctly. So there we go, that is Bill's Fibonacci program working perfectly. So the thing runs Fibonacci, and actually right now it's running the diaper test program because I film things out of order and I'm just warming the thing up for the day and running the test routines on it just to make sure that everything's working good. That bell tells me that things are going well. But it does run Fibonacci. However, Fibonacci Doom does not make. So what are the next steps towards going from Fibonacci to playing Doom?
When Doom loads, the first thing the G-15 actually loads into memory is a loader program. Its job is to load the following 18 blocks off of the tape into the Bendix's memory lines. After the loader program, the tape has about 2,000 lines of data, which are just those waveforms for the notes required to play the music. I'm not sure how many inches, feet, or yards of tape that translates to.
A lot. A whole lot.
After all the note data comes what I call the song data. Those are, once again, they're just a bunch of numbers that get loaded into memory, but each number encodes what note to play, a second note to play, whether to play it on output line 2 or output line 3, and then finally a delay, how long the note should play before the program moves on to the next piece of musical instruction. It's basically the score for the song written in computer code. In typical G-15 fashion, because I ran out of space, the final program that actually plays the song gets written to the line where the loader program lives and replaces it. So the loader program's very last instruction is to replace itself with the main program and then jump back to instruction 0, where now the main program has been loaded and starts executing.
Like you said, you used pretty much all available memory just to get this done, and even then it was still tight, right?
Yeah, I did use almost all of the space on the G-15. Each line is 108 words. The song data is 107 words long, so I have 1 word left over there. I had 18 lines to hold note data. Of those 18 lines, 15 of them hold 2 notes each. The kick noise and the snare drum noise each live on 1 line by themselves. 1 line is all zeros. I have to copy those zeros onto the output lines to play silence, to quiet a note when I don't want it to play any longer. And finally, the player subroutine and the song program is 73 words long on line 0. That's 73 out of 108, so there is a little bit of breathing room, but we squeaked in there.
The journey was long and arduous, but I had some proper slayers on my side like Bill and Lloyd and Paul, and together we have proof positive right here that Doom will run on absolutely anything, including the oldest running digital computer in North America. Just flip it to go and we can rock out. Yes, that's what I'm talking about. Bobby Prince, I hope we did you proud, man. E1M1 will go down in history as one of the greatest pieces of video game music ever created. Also, Mick Gordon, Andrew Holschult, y'all better watch out. Bill and Usagi are on the scene, and I'm expecting that call from id any day now, because who can resist having the greatest piece of E1M1 in the newest Doom game? So I want to thank you all so much for watching, and I hope to see you in the next one. In the meantime, I'm gonna rock out.